Hello everyone, welcome back. In this particular video, we're going to look at the mechanisms of nucleophilic acyl substitution. Now, we've already previewed what the nucleophilic acyl substitution reaction is, but very similar to nucleophilic addition, where the mechanism depends on the reaction conditions, whether the conditions are basic or nucleophilic versus acidic. The mechanisms are different, and the same applies to nucleophilic acyl substitution. The, the course of the reaction or the mechanism really depends on the reaction conditions, whether we are under nucleophilic conditions or we are under acidic conditions or we are under basic conditions versus acidic conditions. The mechanism is different under both of these conditions. So I've chosen some examples here to basically walk you through the mechanism under both scenarios. In the first case, we're looking at a reaction that's going on under strongly nucleophilic or basic conditions. Notice I have sodium methoxide. So that's a strong base, strong nucleophile. So we are doing the reaction using a strong nucleophile here. And our starting material is an acid chloride. And I've just kept a general R group here with a chlorine on it. Now, the product of this reaction would be an ester. So notice how it converts one carboxylic acid derivative, an acid chloride, okay, an acid chloride into another carboxylic acid derivative, which is an ester. And we are basically substituting the Cl with the OCH3. Now, the mechanism of this reaction, when a reaction is going on under basic conditions, it is very simple. It is a two-step mechanism, which starts with the initial attack of the nucleophile on the acyl carbon. So we have our nucleophile, and the first step is going to be the nucleophilic attack on the acyl carbon. The pi bond opens up, which lands electrons on that oxygen. So we will make a tetrahedral intermediate here. You're going to have OCH3 connected to that acyl carbon, or what was the acyl carbon, and the chlorine is over there. So we make the tetrahedral intermediate, and then the tetrahedral intermediate collapses down. So this is the tetrahedral intermediate. So there's the attack. Then we have the tetrahedral intermediate, and then we basically have the collapse of TD, okay, the tetrahedral intermediate. That's going to collapse. And as it collapses here, because chloride is a good leaving group compared to a methoxy group, the chloride is what's going to leave here. So the chloride leaves, and that would give us the ester product plus the chloride ion. So over two steps, which involves an initial nucleophilic attack and then a collapse of the tetrahedral intermediate, we get to our product. Now, in certain cases, you might have to do a deprotonation step after this, and we will see such examples later on. Okay, but for the most part, it is pretty straightforward. Attack by the nucleophile and collapse of the tetrahedral intermediate. Two steps get you to the product. Now, when you go under acidic conditions, and very similar to what we saw with carbonyl compounds, acidic conditions are used for weak nucleophiles. Notice our nucleophile here is water, which is a weak nucleophile. And what's happening here is, again, you're converting one carboxylic acid derivative, an ester, into a carboxylic acid. That is what's happening in this reaction. The OCH3 here is substituted by an OH, and this OCH3 comes out as methanol. So under acidic conditions now, the mechanism is more involved. There are a lot more steps to the mechanism. And the reaction here, the mechanism, it starts with an initial protonation, okay, of the starting material. This gets protonated. So we have toxic acid here, which is basically a source of protons. So that's para-toluene sulfonic acid. So essentially what happens in the first step is you do an acid-base reaction between the ester or the carboxylic acid derivative and the acid. Now, there are two oxygens in the carboxylic acid derivative here, which is the ester here. We have what's called the acyl oxygen, which is the double bonded oxygen, and we have the ester oxygen. Now, in all carboxylic acid derivatives, the acyl oxygen is the more nucleophilic or the more basic of these two. Now, it doesn't matter whether it's an oxygen or not. The acyl oxygen is always more nucleophilic and more basic. So that is what gets protonated in this first step. So the acyl oxygen goes and grabs the proton. I'm going to write that here. The acyl oxygen is more nucleophilic or basic. Okay, that is what initiates the reaction. So the acyl oxygen is going to get protonated, which gives us a protonated ester here. And plus, we're going to have the OTS minus, the conjugate base of the acid that we're using. In a subsequent step, or in the next step, this is where the water molecule shows up. Because again, realize that what we've done here is we've converted this poor electrophile or a weak electrophile into a good electrophile here, because this protonated ester can do resonance now. You can push electrons that way, and you can draw a resonance form where we have OH, OCH3, and a positive charge. So we have a resonance form where we have a full positive charge, a formal charge on that carbon. So that enhances, so the protonation enhances the electrophilicity of this acyl carbon. Something very similar to what we saw in case of carbonyl compounds. So because of that, now in a subsequent step here, the water molecule, which is a poor nucleophile, it can attack the acyl carbon. Now you can show the attack on this resonance form or on that resonance form. And if you're showing it on this resonance form, you're going to show the simultaneous movement of the pi bond here. So let's just show it on this resonance form here. They're both resonance form. They represent the same molecule. Okay, let's just show it here. And so essentially after that step, we will get OH, OCH3 with the water molecule connected to that acyl carbon. And now if you look at it, in terms of the product, we have to get rid of the methanol or the methoxy group here from the starting material as a methanol. And right now, whenever you have an intermediate here, like this, you're always going to do a deprotonation. And since we have water around, the deprotonation is easy. So you can imagine a deprotonation step where another water molecule comes in and deprotonates that intermediate. Okay, it's going to pick up those electrons and deprotonate. That would bring us to the next intermediate, where we have the OH, have the OCH3, and we have another OH here. All of them have lone pairs to them. And plus, it's going to create acid because we just removed that proton. So more hydronium ion is formed. And from here, when you have this intermediate in presence of acid, in principle, all or any of these oxygen atoms can be protonated. All of them would not be protonated simultaneously because that would land a lot of positive charge on the molecule. You would have a species with three positive charges to it. That would not happen. But any of these oxygens can be protonated. Whenever this oxygen of the methanol group is protonated, okay, whenever that oxygen is protonated, the methanol oxygen, it will take us forward to the next step where we'll have RCOH, we'll have OCH3. This oxygen is now protonated, has one lone pair, has a formal charge, and then another hydroxyl group here. And now if you look at it, our methoxy group in the starting material has been converted into like an oxonium looking species. It is a good leaving group now. And so this is where, very similar to what we saw in the mechanisms for carbonyl compounds, and I'm trying to draw these comparisons so that it's easier to understand what is going on here. And once you draw these comparisons, it's easier to remember these mechanisms. So very similar to what we saw in the case of carbonyl compounds, one of these other oxygens, it can use its lone pair to push out that methanol. And that would give us a species where we have RC double bond OH. This oxygen has a hydrogen on it, one lone pair. So I basically flipped the molecule. This hydroxyl is here at the top now, and plus we have methanol. So the methanol came out here. The methanol was released from the molecule. And then one final step where a molecule of water comes in and deprotonates that carboxylic acid, or the protonated carboxylic acid. That's the conjugate acid of a carboxylic acid. If that is deprotonated, we will get our carboxylic acid molecule and regenerate the hydronium ion or the acid. And again, notice how we started the reaction by using an acid, and now we've regenerated the acid. So overall, these reactions are catalytic in acid. You don't need a lot of acid here. And these reactions are completely reversible. So that means you can start from an ester and water under acidic conditions to get a carboxylic acid and methanol, or you could go back. You could start from a carboxylic acid and methanol or an alcohol. Now, I've written a specific molecule here. Read this as some alcohol. That's just an alcohol. So you could start from a carboxylic acid and an alcohol under acidic conditions to create an ester or to synthesize an ester. And that's how esters are synthesized. They are synthesized by the reaction of carboxylic acids with alcohols. Okay, so that's the mechanism of nucleophilic acyl substitution. And as you can see, the mechanism varies greatly when you go to like an acidic medium. There are a lot more steps. There are a lot more proton transfers, so like protonation, deprotonation events that happen. Under nucleophilic conditions, the mechanism is pretty straightforward. Now, one very important thing to remember in these cases, in any of these mechanisms of carbonyl compounds or carboxylic acid derivatives, reactions of carboxylic acid derivatives, is that when you write a mechanism, if you're operating under nucleophilic or basic conditions, you will never generate, okay? Now again, there are exceptions, but you will never generate a species with a positive charge on it. Like there would not be intermediates that are like strongly acidic in nature. And similarly, when you are operating under acidic conditions, you would not generate a species which is strongly basic or nucleophilic in nature. We do not have like any negatively charged species in this mechanism, except for this tosylate, which is a very stable conjugate base. So that's fine. So that's not a strong nucleophile or a strong base, but you will not have a strong nucleophile or a strong base. So I cannot have a deprotonated alcohol like an alkoxide under these conditions. And I'm not going to have like a protonated species, like a strong acid under the strongly nucleophilic conditions. So I hope that helps. We're going to see several other mechanisms which are for the reactions of carboxylic acid derivatives in the upcoming videos. Bye.